In this video, we're going to take a look at our depth-first search. The depth-first search is going to be in a way similar to the breadth-first search in that it takes in the same sort of data, a source and a target, and it's going to iterate through until it finds the target or it's iterated the whole graph. The main difference is how we iterate, right? As I mentioned in the first video on breadth-first and depth-first search, with the breadth-first search, we search all of the different neighbors each time as we continue on through. Whereas with the depth-first search, we kind of follow one path all the way through, then we move on to the next path and follow it all the way through, then we continue on from there. With this sort of process, there's a few different ways that we can implement it. I'm going to show you a recursive approach since it mirrors mostly the binary search tree approaches we've seen so far, so it'll probably feel pretty familiar overall in terms of the process that we're using. So let's take a look at how this will generally work. We're going to have two functions, as we often do with recursion. The first will be our DFS function, which is going to take in a source and a target. And what it's going to do is it's going to keep track of everything that we've visited inside of a dictionary, much like our breadth-first search. And it's going to do a call to an auxiliary function, which is going to do the actual recursion itself. And that is going to require the visited as well as the source. And what I'm going to do to start off with this is I'm going to show you how to do this just like iterating and seeing how we iterate. And then we're going to take a look at how we actually search for the target. So we'll do our iteration first, then we'll do our search. So for our iteration in DFS aux, what we end up having is basically just the visited as well as the source. And what's going to happen is we're going to set the visited at s to be true. We're then going to print out the value of s. Then what we're going to do is we're going to say for I inside of the adjacency to s, if I is not in visited, right? Then we're going to do a recursive call to DFS aux, and we're going to do it recursively using visited as well as the value I. So you see we just recursively call with the thing that's adjacent to it. So basically each time this will continue to recursively call until it reaches the end, and then it goes to the next node and recursively calls down its branch until we reach the end of that, right? So that's the main process that we see here. Let's take a look at how this actually prints in our DFS. So if I were to do a DFS from, say, 0 to 4, when I run something like this, what you'll see is that we get the following idea. Do you see it goes 0, 1, 3, and then it goes 4, and then 2. So it starts at 0, it traverses to 1, and then traverses from 1 to 3, 1 to 4. So do you see that it went all the way down that path? It started from 0 to 1, and then it continues down 1's path until it reaches the end of it. And then it goes to the next node, which is 2. The next thing after that would have been 2 to 4, but we've already visited 4 from our previous iteration, so we don't need to do it again. So we just stop at 2, and then we're done. So you see how that goes all the way down one branch and then goes to the next branch and starts iterating down it, skipping anything that it's already visited, right? So that's the process that we have here. Now from here, we can take a look at actually adding in a target for our search. So I'll do the 0 to 4 again. And what we're going to do is we're going to set up how we can actually search this as a target. So the modifications here are not too many to get this up and running. So basically, DFS aux is now going to take in some form of target. And what it's going to do is it's going to say, so visited at s equals true. And then what we want to do is we want to check to see if the source is equal to the target. If it is, then we're going to return true. I just realized source I'm saying is s, so we'll say s equals target. We'll return true. And I'll just keep this print here just so we can see it print as it goes, because it makes it a bit easier to sort of see how the search ends up running, right? So we'll say if s equals target, we're going to return true. And then what happens here is we set up the adjacency. We do the if not visited. And then what I want to do is I want to just add an if statement here to check the result of this. So if this ends up being true, then I just want to return true. I want to stop searching and return back. And then basically outside of this, we'll return false. So if we don't end up returning true at some point, we'll end up returning false on our default case. And then what we'll do over here is we'll just change this up so that this returns back the result of the DFS auxiliary. And that's all we need to do to turn this into a search. Let's take a look and see. So some different things that we could check from 1 to 4, we should be able to reach. So this one should work fine for us. So we'll take a look here. And I see here that I've just missed my one argument here. There we go. And as you can see, it goes 0, 1, 3, 4. Once it reaches 4, it prints out true because it's found the value that it was looking for. I could say from 0 to 2. You'll see with this case, it has to go all the way down to 4, and then it goes to 2, and finally returns back true. So that one is a lot of different checks to get there, right? If it's something along the path to 0, it will find it faster, like 3 or 1. And if it's looking for itself, that's a nice and easy case, right? You'll see that it's just 0, and then it returns back true. And then finally, we can check to see something not in the graph, like 5. 5's not in the graph, can't reach it, so it ends up giving us false after searching the whole graph. Final question here is time complexity. How does this fare versus our depth first search? And overall, it's about the same in terms of time complexity. There's some small differences as we go through, but overall, when you look at the full time complexity, it's about V plus E. It's time complexity as well. So that gives you your two different searches that you have available to you, breadth first search and depth first search. Generally, I wanted to introduce these searches for a few main reasons. The first is that we're going to see them used in other sorts of algorithms. So it's important to understand how these work at a baseline before we actually move on to using them in different cases. And the second reason is that sometimes you may be asked these kind of things for like an exam or interview, something like that. So just knowing the general baseline algorithms is pretty helpful. I found that generally it was a bit harder to find things like a depth first search that actually searches for a target. A lot of people have an iteration online, not as much the actual search for the target itself. So I wanted to give this as an example as well so that you could see how you actually terminate on search for target as well. So with that, you now have your two searches out of the way and we can move on to some different algorithms. Thanks so much for watching. I'll see you in the next video.